Hello everyone, welcome to Design Verification Made Easy. In this section, we will exploring number system conversations. Today we will focus on decimal conversions, understanding how to convert the decimal to binary, octal, hexadecimal step by step. Let's start together. Why do we need number system conversions? Because computers understand only binary languages like an zeros and ones, but human understand only decimals. So that converting between the number systems helps in the programming, debugging and making calculations easily. And in the digital electronics, it is used in the memory circuits and error detection purpose also. Types of conventions. There are four types of convention: decimal convention, binary convention, octal convention and hexadecimal convention. In the decimal convention, one is decimal to binary, decimal to octal, decimal to hexadecimal. Next, binary convention, binary to decimal, binary to octal, binary to hexadecimal. In the octal convention, octal to binary, octal to decimal, octal to hexadecimal. In the hexadecimal convention, hexadecimal to binary, hexadecimal to decimal, hexadecimal to octal. These are the types of conventions we have. Now let's understand how to convert a decimal number into binary. Decimal numbers use digits from 0 to 9, but computers understands only zeros and ones, as I said before, which is binary. So we need to convert decimal numbers into binary. The process is simple. We keep dividing the number by 2 and note down the remainder of each time. Once we reach 0 when we are dividing, we just write the remainder in the reverse order from down to up, and that gives us the binary equivalent. Previously, we saw an example where we converted only integer part of a number such as 27 into a binary number. But what if the number has a fractional part like an 0.45, 0.75? In the next slide, we will see how to convert the decimal fraction into binary. Before we look into example, let's understand the basic rules of converting decimal fractions into binary. We use the multiplication by 2 method, which follow simple steps. Multiplying the decimal fraction by 2, note the all integer parts 0 or 1. This becomes the next digit in our binary results. Take the fractional part and multiply it by 2. Repeat this process until you reach the fraction part. This method helps to converting the decimal numbers into binary for more efficient way. Now let's apply this method to convert the 0.45 decimal to binary. We start with 0.45 multiply by 2 and we got 0.90 taken as 0. Next 0.90 into 2 is equal to 1.80. Take 1. Remove the 1 and continue with 0.80. 0.80 into 2, 0.80 into 2 equal to 1.60. We take 1 with continue as a 0.60. Like that we did for all. When we see repetition pattern for the 0, 1110, so final representation of binary of 0.45 is 00, 1110, so on. This method works for any decimal fraction and recognize the repetition pattern helps to understand the previous limitations in the digital system. In the previous example, we've seen the decimal to binary conversion. Now we will see the decimal to the octal conversion. Same as in previous binary. But only the difference in this is only we have to do the multiplication and division with 8. When it is coming to the fractional part, we will do the multiplication with 8 with the fractional part, and integer part we will do the division with 8. We will see in the next slide the example. Now let's take the example of the converting decimal number to octal. First, for the integer part, we have to take 127 and divide it by 8. 127 divided by 8, coefficient is 15 and remainder is 7. For same as in 15 divided by 8, coefficient is 1 and the remainder is 7. 1 divided by 8, the coefficient is 0 and remainder is 7. The result we have to take from the bottom to top, means 177. Like an increasing order, we have to take the result. For the integer part, 127 base 10 is equivalent to 177 base 8. Same like and for the fractional part, 0.375, we have to do the multiplication. Here we will do the division, here we will do the multiplication. The result is 3.0. Integer part is 3 for this one and the fractional part is 0.00. Thus the octal number equivalent to the 0.375 is 0.3. So the final result of 127.375 base 10 equivalent to 177.3 base 8. It is equivalent to the octal number. We followed these steps in the previous example, dividing the integer part and reading the reminders from the bottom to top. And for multiplying the fractional part and reading the result from the top to bottom, we get the octal equivalent. Now let's see the decimal to hexadecimal conversion. In the decimal to hexadecimal conversion, we will do the division by 16 and we will repeat this process until the coefficient becomes the 0. Now let's take a small example for the conversion of the decimal to the hexadecimal. 127 divided by 16. 16 is nothing but the hexadecimal. When we are doing the division for 127 divided by 16, we will get a coefficient as 7 and the remainder is 15. And 7 divided by 16, we will get the remainder is 7 and the coefficient is 0. 127 base 10 is equivalent to 7f16. This 7f16 is f is nothing but the 15 in the representation of the hexadecimal. Based on these steps only, we solved the previous example for the decimal to the hexadecimal. So that's the reason we divided that one with 16 and record the remaining until we receive the 0 and read the remainder in the reverse order to get the hexadecimal equivalent. Today we covered number system conversions. I hope this video was helpful. If you have any questions or doubts, feel free to comment me. Do not forget to like, share and subscribe. See you in the next video. Thank you for watching.